Hello, everyone. TCS seminar at the Jagiellonian University. Today, our speaker is Paul Bastide. So Paul studied at ENS Rennes, and now he is at the first or second year of his PhD.
Yes, second year.
So that you're making your PhD in two places. It's quite complex. So Paul stays in LaBRI in Bordeaux and also at TU Delft in Netherlands. And today we're going to hear about his project on poset saturation problems. Thank you for joining us, Paul, and the floor, the Zoom is yours.
Thanks a lot for the nice introduction, and thanks for the invitation. So yeah, I will talk about skipless chain decomposition, and then I will talk about poset saturation and show why we are interested in the skipless chain decomposition. But first, something that probably everyone in this audience now knows. What's the Boolean lattice? So Boolean lattice is just the subset of 1 up to n, and we consider the order to be the inclusion order. And yeah, this gives a poset, as you all know, and this is how I will present posets in general during this talk, so just by the Heiss diagram. Yeah, I guess you also all know what a chain is in a poset. It's just a set of elements where every two is comparable, and an anti-chain is the opposite. It's a set of elements where every two is not comparable. But I guess one thing that's maybe more specific in this talk is what's a skipless chain. So a chain is said to be skipless if between any two elements of your chain, you could not add something such that it's still a chain. So for example, the picture on the right, the free red element does not form a skipless chain because I could have added either 1, 2 or 1, 3. So if I add one of the two, then now it's skipless. For any two consecutive elements in the chain, I cannot find someone in between. Okay. Just note that being skipless doesn't mean being maximal. So for example, if I remove the element 1, 2, 3, it's still a skipless chain, but it's not a maximum chain. Okay. So I hope it's clear. Of course, if you have any question during the talk, just feel free to ask about definition and stuff like this. There were quite a few, and it's important that you remember what skipless mean. Okay. So I guess one very basic thing in poset theory, it's Dilworth's theorem. It's a link between the anti-chain size and the size of the chain decomposition in a poset. It's very well known. It's equivalent to Menger theorem in graph theory. It's probably the first thing you will see if you take any lesson on poset. So it just tells you that the largest anti-chain is also equal, the size of the largest anti-chain is also equal to the size of a chain decomposition if you want to decompose your poset into a bunch of chain. And so it's natural to ask, can we improve the Dilworth theorem in general? And for example, can we ask those disjoint chain in the chain decomposition to be skipless? So maybe I can let you think about it a bit. So is it true that for any posets, if I look at the size of the largest anti-chain, then I can always find decomposition using this number of chain and the chain are skipless? Well, sadly, the answer is no, because of this poset, for example. So this is a poset where the anti-chain is of the maximal anti-chain is of size 2, for example, the two top elements. And still, there is no skipless decomposition of size 2, because one of the chain, you need to believe me a bit, but one of the chain need to take the three bottom element, these three elements, sorry. And then you need two different chain to cover the rest because they need to be skipless, right? So sadly, it's not true. Okay, but now what if we see this poset embedded in the Boolean lattice? So what I mean by that is just I take arbitrary embedding. So I will consider this one for this example. Now, is it true that using the structure of the Boolean lattice, I can find some kind of skipless decomposition? And it happens to be true, because in the Boolean lattice, if you see, there is also this element, 2, 4. And now I can just find two skipless chain in the Boolean lattice that covers my poset, okay? So we can ask ourselves, is it true in general? Can we do it for some poset? And what kind of embedding do we need to take in order for it to be true? And it happens to be true for any poset and any embedding. So what does it mean? It means that if I take any family in a Boolean lattice, and I look at the number of chain I need to decompose them, just chain, not skipless, then I can find a covering of this family in the Boolean lattice still, such that the chain are now disjoint and skipless. Okay, so I apply Dilworth's theorem, I get a bunch of chain that are not skipless, non-disjoint, and I can find a covering, so a larger family, but in particular that contain all my former family, and that is composed of disjoint skipless chain. Okay, so it can be formulated in the two-way here. It's exactly equivalent. I hope this is clear. And so this is something that has been studied a bit already, this kind of thing. So a special case of this theorem have already been proved in 2001 by Lehmann and Round. We'll prove the special case that I will show later, where all the chains are size 2, and they start and end in the same layers. And Dufust Owen leader proved not too long ago the special case when the family is convex, which if you don't know what convex means, it's not that big of a deal. But yeah, just to mention that those things have been studied in general, the skipless chain decomposition. Yeah, so this is a drawing of what happens in the special case of Lehmann and 1. So for example, you have 4 chains, they're all of size 2. So the chain are just this matching, okay? And they all start in some layer and end in some layer. And what this lemma says in the special case is that you can find, of course, the anti-chain size is just the number of people in the top layer. You can find a chain decomposition where the chain are skipless and are going from one of the top element to the bottom element. But already here, it's non-trivial in the sense that you cannot preserve the matching. It's possible that you need to link some top. For example, the second top cannot be linked to the second bottom, but needs to be linked to another one in order to find this nice skipless decomposition. Okay, so I guess this is the basic idea in this structure. And just to give a very, very quick glance at what the proof looks like, because the proof is quite technical. What we do is that we just deform a bit what happened in the special case of Lehmann and 1. And what we do is that we put one of the elements just below. So this element can be anywhere below this 3 here, but all the other elements are on the same nice decomposition on the same layer. And the chain are always of size 2. But also we need to add something more. We need to add that there is some element in the middle. So for example, those 3 elements that are already covered by our chains and that we still want to keep in our decomposition once we add one element in the middle layer to make this chain kind of skipless. Okay, so maybe something they took like this. This is just using kind of the base argument of Lehmann and Round, but in more there is more technicality to check. There is a clever double counting argument in order to see that you have enough people in the Boolean lattice to make this works, and then you use Menger theorem in order to conclude that you have enough connectivity for this to happen. And once you have this lemma, then you just need to plug it in inductively and trying to fill up all your chain, trying to find some nice substructure. If all your chain are not skipless, you will be able to find some nice substructure on which you can apply this lemma, and you get a new element, and you can apply it again, until once you cannot apply it, in fact, it just means that all your chain are skipless. This is also non-trivial, but this goes through with a nice induction. And so, yeah, this was just to give a glimpse of the proof, but I will not talk too much about the proof. I will try to explain why this result is interesting in itself. So all these things that has been proven by Lehmann and Round and Leader and stuff in the past, it has been used for computation of function on the Boolean lattice. If you have some continuous function on the Boolean lattice and you are looking for some value of this function or something like that, you use this kind of chain decomposition. I don't know too much about it, but I know that it's quite used in this field. But for now, we'll focus on another problem that's called poset saturation in general, but we'll focus even more on anti-chain saturation now. Okay, so I will take a family in the Boolean lattice, and I would say that it's k-saturated if it has no anti-chain of size k. But for any element that I add to my family, then it contains an antichain of size k. That's why it's called saturated. It's like maximal for not containing an antichain of size k. Okay, maximal for the inclusion of not containing an antichain of size k. Okay, that's just the definition. And then some extremal combinatorics people are interested in computing the minimum size of such family. Okay, so what's the minimum size of a family that is maximal for the property not containing an antichain of size k? Okay, hope this definition is clear. Okay, let's maybe do an example. So let's take the hypercube of dimension 3. And let's look at this red family. So this is just a chain, right? So as it's a chain, it doesn't contain any antichain of size 2. Perfect. And you can see that if I add any of the gray element, then it starts containing an antichain of size 2. So this family is 2 saturated. It doesn't contain any antichain of size 2, but if I add an element, then it does. Okay. And it's a family in the hypercube of dimension 3. So this means that the SAT number, this minimum size of family in the hypercube of dimension n, that does not contain an antichain of size 2, it at most 4, because I find an example of family of size 4 that satisfies all the conditions. Okay. And in fact, this construction using a chain, you can see quite quickly that it generalizes, right? If I take an hypercube of dimension 3, I take a maximal chain in this hypercube. Now it still doesn't contain antichain of size 2, but for any element that I add to the chain, there will be an element of my maximal chain in the same layer. So those two will be incomparable, and you will create an antichain of size 2, right? Okay, just because your chain is maximal. So whatever you add, create an antichain of size 2, right? And this generalizes a bit further. So if you have k to be any integer less than n, then you can take just this joint chain up from the top and the bottom element. So you take k minus 1 disjoint chain, and for the exact same reason, if I take any other element, it's in the same layer with the k minus 1 element disjoint maximal chain, right? So it creates an antichain of size k. Okay, that's just like the first, if you think about it for a bit, that's the first construction naturally you will come to. And the size of this construction is what's written down here. And okay, so that's the first observation. And people tried to see if this was optimal. And they didn't manage to prove the exact value for all k's, but they still managed to prove that it was optimal for k is equal to 2, k equal to 3, and k equal to 4. So they conjectured that it was at least the right asymptotics, right? So this was roughly n times k minus 1, which is what you have here up to some very small function of k, okay? And then some other people came along and computed the value for 5 and 6. And maybe interestingly, 5 is not satisfying exactly this condition. So which means that the 6 is not satisfying exactly this. So which means that the optimal family for 6 is not exactly this construction, it's something else. But still, they conjecture something a bit stronger, that even conjecture that it's not just the asymptotics that is right, it's even the constant, the second term after this linear term is only dependent in k, and there is no dependency in n. Okay, so it's even a stronger assumption, even though we know that after 6, this construction is not optimal. Okay, and I will try now to at least give you a glimpse. I will try to do a complete proof, but I will be happy if you get at least the gist of it, that both of those conjectures are true using our lemma. And if I want to write up the proof, I think in the paper you can prove both conjecture. Once you have the lemma, the skipless decomposition lemma, you can write it down as a proof in half pages. So it's quite a strong result. So it solves both the conjecture. Okay, so the setup is like this. You have your hypercube of dimension n. You consider some family that is k saturated, and you consider decomposition just using Dilworth's theorem of this family. So this composition is obviously using k minus 1 chain, right? Because it doesn't have an antichain of size k, it's k saturated. And it cannot use only k minus 2 chain, because otherwise adding one element will never create an antichain of size k. It can only create an antichain of size k minus 1. Okay. And this family, because it's saturated, it has to be this maximal property, which can be stated like this somehow, that if I look at one of the chain of my decomposition and I look at any element that I could have added in the chain, such that it's still a chain, right? Any element of the poset of the hypercube, such that I can add and it still like continues one of the chain, then it should already be in my family. Otherwise, this family F will not be maximal, right? So for example, if there is some element here under the end of this chain, right, that's still under this this X, that is included in this X, then it should be already in the family somewhere, maybe in one of the other chain, because otherwise I could just add it and it's not maximum, okay? Well, from this small observation, we can prove this claim. It will be kind of useful. It just states that if I look at any of the chain in my chain decomposition, then it should not start too high and it should not end too low. And this too high and too low is this L here, which is defined a bit weirdly, but you will see why we define it like this. But roughly, what's important is that this L is of size is roughly log K, right? So you take any L that satisfies this inequality, and roughly if you take log K, this is good enough. Okay, so why is that so? So let's come back from the observation above, and let's try to apply it to some chain that ends up too high. So I have a chain here such that the minimal element is some X, okay? And X, the size of X is at least L, okay? Then I can look at what happens in between X and the empty set, right? So this is a sub-Boolean lattice. So let's draw it here. You have a sub-Boolean lattice of dimension at least L that is in between X and the empty set. Okay, by this argument above, it should be completely filled by element of F, right? Because if there is some element gray here that is not in the family, I can add it and I still have the same number of chains. So by Dilworth, I still do not contain any anti-chain of size K. Okay, so this family should be full red, but we choose this L such that in the middle layer of this family, of this hypercube, sorry, in the middle layer of this hypercube, there is more than K people. Okay, so as there is more than K people, it cannot be all included in our family, or our family will already contain an anti-chain of size K, which will be a contradiction. So you have both. On one side, it should contain everything, otherwise I can increase. And on the other side, if it contains everything, then it's not K-saturated because it contains already an anti-chain of size K. So it's quite simple. And that just proves that all our chain needs to start and end low, because of course the other side is the same thing, right? If you look at the top of the chain and the complete set, you have the exact same argument. Okay, so let's just take a step back. What did we prove and how can we conclude with just our lemma? So we have a family that is K-saturated. That's what we proved. We can use some Dilworth to get some chain decomposition. By the claim that we just proved, we know that all the chain in the chain decomposition start at layer some log K and end at layer n minus log K. Okay, and now we use our theorem. And it says that our family is coverable with K disjoint skipless chain, of course. And in fact, because our family is supposed to be maximal for inclusion, this cover is a partition, right? Because if there was any element that were not in my family, again, same reason, I could just add it. I still have a decomposition using K minus one chain. There are even skipless, but that I don't care for this argument. It's using only K minus one chain. So using Dilworth in the opposite direction, I get that I still do not contain any anti-chain of size K. Okay, so this theorem tells us that F is in fact a partition into K minus one skipless chain, right? And we know that all the chain needs to start at layer log K and end at layer n minus log K. So we could just compute the number of elements, right? The number of elements for a given chain would be roughly n minus 2 log K. And you multiply this by the number of chain, which is K minus 1, and you get this value here in blue. And this is already proving both the conjecture because you get the asymptotic, of course, and you get that the second term is only dependent on K. And it's in fact giving something stronger because this K log K is optimal. You can do more, you cannot do better than K log K, and now you're only fighting for the constant. So it's even more pinpoint than what the conjecture opt for. Okay. And once we realize that, we say, okay, we are very close to getting something exact because we only have this constant to tackle now. So can we get something exact? And so let's see what's happened and what still needs to be done. So basically, if I look at any K-saturated family, it should look like this. With our result, roughly in the middle, I have this nice chain, and then there are the thing that happened between L and the empty set, and the thing that happened between L minus L and the full set. That I don't know exactly what happens, but I ended up, knowing everything in the middle. Okay. And it happens that some people prove a better lower bound than the one I show you with just disjoint complete chain. And they prove something slightly better, but still it was not clear that it was optimal. And maybe now we need to enter in some notion of set theory and stuff like this. So I define the shadow of, if I take a subset of some of the Boolean lattice, let's consider that the subset is in some given layer T, then the shadow of this set is just all the elements that are below in the Boolean lattice. So included strictly and in the layer T minus 1. Okay. And also I need to define the initial segment of codex. Okay, so there is a typo here, but okay, this is the initial segment of codex, sorry. To be, you look, if I take two elements, how do I compare them? I look at the largest value, and I try to find the one that are if they have the same largest value, I look at the second largest value, etc., until there is one that contains a largest value, IF largest value that is higher than the other one. For example, what's a good example? Yeah, for example, 1, 2, 5 would be before anything that contains only the element up to 1, the element 1 up to 4. So in this order, for example, 1, 1, 3, 4 would be before 1 to 5, right? Even though it would be the opposite for the lexicographic order. So this is the complement of the lexicographic order in some ways. And it has a nice, it's well studied because it has a nice property, which is it minimizes the size of this shadow place over there. So it's quite understandable by the way I describe it. If I look at the all element that contain only the element 1 up to 4, then all the shadow is just the subset of element that still contain only the element 1 up to 4, and this minimizes the size of the shadow. Okay, and why are we interested by things like this? So we have our chain coming from the middle layer that have a very nice structure. We know that we have k minus 1 of them at some point. And then what we would like is to choose those k minus 1 that we ended up with, such that we cannot continue the chain. Because if we cannot continue the chain, this means that we have a lower amount of people in the layer below, and our family is smaller. So we try to avoid having a nice continuation, actually. Okay, so we try to minimize this shadow somehow. So that's Kruskal-Katana, sorry, also well-known theorem that says you that this initial segment of codex minimize the size of the shadow. So that's this F is, you need to see it as all the subset that you could use to continue your chain, right? And it happens to be not exactly what we want, right? Because let's say we have some structure like this, and we want to continue the chain, right? It's more than just considering the size of the shadow. What we want is to be able to find some matching here, right? And that continues the chain, and we want to minimize the size of this matching, because if the size of this matching is very small, that means that only a few chain can continue, and we are using very few elements. And it happens that this is also minimized by the initial segment of codex. Okay, so that's something we prove. It's also looking quite a lot like Kruskal-Katana, even though the proof is not exactly the same. And we thought at first that it has probably been proven somewhere, but we didn't find it. So if anyone knows about any reference where this has been already proved, we'll be very happy to just use that. Yeah. And just to give an example of why it's not as simple as just using Kruskal-Katana, this maximal matching is not always just the shadow, right? So if I look at this family, so I have all the sets of size 3 of 1 up to 6 and 1 to 7, and this is the shadow of this family. Then you see that I cannot both use 1, 7 and 2, 7, right? Because there is the two of them are only linked to 1 to 7. So the maximal matching, we've only used one of the two, and we will not use all the shadow. Okay, just something to keep in mind that it's not exactly the same. And yeah, okay. So using all this was just very vague and end wavy thing. Using all this, what we can do is actually prove the exact value of the saturation number nk, as long as we have this very mild condition on n and k, which is n is larger than 2L, which are, if you remember, L is like log k, so just stating that n is larger than 2 log k, which is very, very mild. Yeah, and we have this very ugly statement, but all those constants can be computed. And yeah, it's just the size of this maximal matching, right? Each time we try to minimize the size of this maximal matching. Okay. And this is quite surprising, actually, to get the exact value. We'll see later why. And this is still open for this small case of n less than 2L. And the idea is just that we cannot use this nice decomposition in the middle now because the top and the bottom are too close. So this creates some border issue, and all our technique doesn't work. So it'd be interesting to tackle this problem, but I think it will be quite harder to get just to small cases. Okay. And just to get a very small glimpse, we also needed to improve the upper bound in order to fit, because this is a general lower bound that's always true. Even for smaller value, but in order to fit with the upper bound, we needed to improve the upper bound, and this used some canonical decomposition that is also used in Kruskal-Katona. We'll not go into too much details, but they are not exactly the same as Kruskal-Katona, so we needed to prove some new nice binomial decomposition that could be useful maybe somewhere else also. It's quite nice, but yeah, okay. So that was it for the for the anti-chain saturation. And now I would like to talk about the more general problem of saturation, poset saturation. So the poset saturation would be the same thing as for the anti-chain, instead that now you have a poset. So you fix some poset P, you don't have any induced copy of P in your family, but for any X that you add, then you contain some induced copy of P. Okay, so same thing as before, it's a maximal for not containing P as an induced subposet. And of course, we are still interested in the same thing, the size of the smallest family that is P saturated. And maybe one of the first results is from Morrison, Noel, and Scott, who proved in 2014 that this, for the chain of size k, so ck is chain of size k, this is less than 2 to the some function of k, okay? And a bit before, it has been proven in other setting that, in fact, lower bound hold, which is still up today, I think, the best lower bound that is known, of 2 to the k minus 3 over 2. But it's already interesting that even in this simple case, probably the simplest case, because chain is probably the simplest poset, it's still not known the exact value for a chain of size k. And then this thing has been extensively studied. So this is on the left, you see a list of poset, and on the right, you see all the values that have been computed. And you can see that it is known, the exact value are known for some small posets, but for any poset larger than 5 elements, I think, there is no exact value that is known. So this anti-chain thing is the first family for which we got exact value for quite a lot of elements. Even for chains, still not known the exact value, which is kind of crazy. But yeah, okay. And one of the most recent results, and probably the most beautiful result in the area in the last few years, is this, what can we say in general, right? Because we studied the special case of the anti-chain, they studied the special case of all those kind of posets, but can we say something in general? And the answer is yes. And a group of people from the UK proved that, in fact, you have some kind of general lower bound, which means that either your saturation number is a constant, or it's at least this 2 square root n minus 2, which means that there is a gap. It cannot be log n, for example. It can only be either constant or more than square root n. Okay, so that's quite interesting. And so we saw this result, and we ask ourselves, okay, can we do something? Can we do the same for an upper bound? Can we prove that the saturation number is bounded by some function of n and some function of the poset p. Because technically you were just considering a family in the Boolean lattice, right? So it could be that this set n of some p could be 2 to the square root n, or even 2 to the n over 2, or something weird. We don't know. But we managed to prove that actually it's always polynomial, and it's always at most n to the size of p squared. Okay, so it only depends on the size of p, but it's always polynomial. And in order to prove this, we needed to introduce 2 new parameters that are not known. I asked Piotr and Tom, and they told me that they are not known. So I guess that means that they are not known. It also leads to some nice, interesting question in itself on the parameter. So let me define those 2 parameters. So first, the cube height of a poset is, roughly speaking, you want to embed your poset using the least amount of layer possible. So you want to squish your poset this way first, okay? And then I will need to squish the poset in the other direction. But what I mean by squishing this way, I mean that you can take the dimension that you like. You can take a very big dimension, and you look at the hypercube of this dimension, n, and now you need to minimize the number of layers you use starting from the antiset, right? So you need to use only thing in this in those small layers, right? And you take n large enough such that this h star, this cube height, this height that you use is minimum, okay? And once you minimize this h, you want to keep the same h, so you want to still be able to embed your poset with minimal height, and now you want to reduce the dimension, so you want to reduce the width, and that's the cube width. So once you fix the height to be minimal, now you want the width to be minimal, so the dimension to be minimal. Okay, note that if you define the thing in the other direction, then it becomes simpler, and it's not the same value at all. If you define both to be first to be like minimize the width and then minimize the height, for example, we can very easily show that both of them are linear in size of p, but this is not the case here. So maybe just give one example for the intuition. If I look at the antichain of size 5, I could embed it in the first layer of the hypercube of size 5, okay? But I could also embed it in the first 2 layers of the hypercube of size 4, right? But this is not satisfying our definition, because here I'm not using the minimal h. The minimal h is 1, so I should only be able to use the first 2 layers. And so the width of this of the antichain of size 5 is 5, right? Even though you could embed it in the antichain of dimension 4, of the Boolean lattice of dimension 4, okay? And yeah, I would like to just give you a quick glimpse of what happened and why those kind of definition and parameter are useful in our case. So let's try to see what happens. Let's do some very simple construction to get our saturated family. So what we do is we first take the first h star layers, and we can always take them completely. And that's just from the definition of h star, actually. That's why we define it such that it works like this. And from the definition, you see that it has been defined as, basically here we take the first h star minus p layers, the layer 0 is contained in it, so it's how to say it, we need one more layer to start containing p, so it's just a layer just before containing p, right? And of course we can take all of them, because I'm sure that I still p3 even if I take all of them. And then what we do is we do any completion of this. So one interesting fact to see is that if I give you a family that is p3, then I can do a greedy algorithm and get a family that is p saturated. The algorithm is just going over all the other elements of my hypercube, and you decide to add it only if it does not create a copy of p, right? So I can take any order on the element of my hypercube and just look at them and add the one that are not creating a copy of p. So let's divide my construction like this. F0 is the first layers, and F1 is this completion. Okay, So F0 by definition is bounded by, the size of F0 is bounded by n to the h of p. And the size of F1 will be bounded by h to the width of p. And that's come from just a VC dimension argument, which is kind of cute. Actually, the paper, this is the first part of the presentation was one big paper about skipless chain decomposition. And this part is just a small paper of, I think it's maybe between 5 and 8 pages. And it's the proof in itself could be even shorter. And it's quite a cute proof. And we use the VC dimension. We prove that the VC dimension of F1 is bounded. And it's a bit hard to get the idea through just a presentation, but the intuition is that if I shatter a set that is big enough using F1, then I will be able to embed all my poset P except the maximal element in F0 and still be able to use the element of F1 to be my maximal element. Because if I have all possible kind of relation using the saturation of a large enough set, then I can find exactly the relation that I want for my maximal element, and that works out fine. And so what's the
one question,
sure.
Bounded in terms of what? Just bounded by
constant? It will be bounded by WH of P, this thing, the cube width of the poset. Exactly. I don't think I stated the lemma exactly, but yeah. So the dimension of F1,
sure.
Yeah, the dimension of F1 is bounded by this width of P.
Okay.
So in particular, it's bounded by P squared, because you can prove that the width of any poset with this definition of width, cube width, sorry, is at most P squared. But yeah, if you prove any better bound for the width, then it will improve directly our bound for the poset saturation. So we get exactly this, right? We get that the size of our family is the size of the first layers. So this was n to the h star, and the size of the second layer, using the fact that the VC dimension is bounded and Chow lemma, it's bounded by n to the width of our posets, and you can prove that the height is always lower than the width. So in a big O of things, this is just bounded by the width, just about computing the width of your poset. And yeah, you have general bound on the width that you can derive. So if you want a bound not using this parameter, and with a bit more effort, you can improve this to be quadratic but divided by 4. And it's still widely open if this width parameter could be linear, actually. And it seems to be true. I think I computer check for poset of size up to size 10 or something, and it was true. But then I don't have a proof of this yet. It would be interesting to study, because it will directly improve our bound also. And
what is true? I mean, you write it big O of P, so whatever you computed.
I computed this to be even with a 1. It's less than size of P.
I see.
Yeah. And I think it's true. You see the constant here, yeah, it's probably 1, but it will be interesting to prove any kind of linear relation already and non-quadratic. Yeah. Okay, and maybe just to conclude, I would like to talk about my favorite conjecture in the area first, which is the following thing, that actually the saturation number of any poset is either a constant or it's linear in the end, which is kind of crazy, because if you look at all the table that I showed you, there's like, I don't know, 20 or 30 posets for which it has been studied, and there's still no counterexample to this conjecture. So it's still possible that this conjecture is true. And that's kind of crazy. It could be, but yeah. At the same time, some people also conjecture that the saturation number of a specific poset called the diamond is q10. So these are two conflicting conjectures. But I personally think that probably the saturation number of the diamond is also m. So, but yeah, it's interesting, and we try to tackle this with Piotr and the Krakow group at some point. Yeah, and we didn't manage to solve this for the diamond yet, but we'll see, maybe in the future. And just one very last thing to just show that we don't understand many things about this saturation number. the saturation number of a chain of size 2, it's 1. It's easy to see. You just take your family to be the bottom element of your hypercube. Anything that you add will create a chain of size 2 because it's comparable to the empty set. It happens to be n if you look at 2 C2s. Okay, that's a proof that's a paper, but that's not too bad of a paper. And some people also computed it for 3 C2s and proved that it's at most 14, right? And we don't know. There is no logical explanation of why it's going from constant to linear to constant. It's also known for 5 C2s to be constant, for 7 C2s to be constant. So maybe it's linear for an even number of C2s and constant for odd number of C2s, which could be possible. It could be also possible that just 2 is a very special case and everything else is linear. We don't know. And even though there are very small posets and very simple posets. And yeah. I will conclude on this. Thanks a lot for listening to me.